Oh, Justice, can you hear me?
Yeah, we can.
Yeah, I had what do you call it? Issues, data slash internet slash whatever issues. So, and I just got someone to get me uh some bundle to use. Uh, yeah. Okay.
Have you moved yet?
What did you say?
Have you moved yet?
Yeah, I'm actually in what do you call it? I'm actually in Seattle now.
Oh,
Yeah, of course. But where I am, we've not activated the internet yet. The home internet isn't working yet, so I had to try and
um,
uh, sorry, I'm just using hotspots. Let's wait for a while for the others to hop on. Let's wait for a while. Ah, bro, I've been struggling for the past 15 minutes trying to get data bundle. Now I know how it feels like. I miss the Ghana life. When you don't have bundle, you have to struggle. Yeah, America overexposed me to Wi-Fi, so not having Wi-Fi is a struggle.
for real. If you don't have Wi-Fi, you really struggle.
Yeah,
Like even if you have Wi-Fi, with the policies concerning how their SIM card and all those kind of stuff
yeah,
work, like if you don't
it's so bad.
pay your subscriptions,
Yeah, it's
you
deactivated.
can't even make a call.
Yeah.
Someone can't even call you.
Yeah, I think that's a good thing about Ghana. Like Ghana, you can have zero credits, zero bundle. They can still use your SIM card.
Yeah,
Over here, you
but
can.
not here.
Yeah, very sad. Okay, let's wait for a few people and then let's start. Today we um have a lot to cover, but you have to complete everything on time. I'm even planning we finish everything within like 30 minutes, and then we are out of here. Hello, everyone. Hello, hello, everyone. Hello. Yeah, Prince says hello, hello. Yeah, hello. Yeah. Yeah, but everyone can hear, right? Good, good, good. Let's wait for just like a minute more for others. Yeah. Okay, let's just wait for like a minute for a few others to hop on. Okay, let's wait for like one more minute. Okay, we are actually going to start early because we can't um let me try to connect my devices. So we start. Okay, everyone can see my screen, correct?
Yeah, we can see it.
Okay. Um, Okay, let me hit record and then we can start. Oh, it's already recording? Pause recording, stop recording? I had no idea. Okay, I think it's recording. Oh, it shows at your ends that it's recording, right?
Yeah.
Okay. So yeah, so we actually had just have a few things to go over today. Um, but first of all, like recruiting is like in 2.5 months. Because you're already like almost in June, so you have full of July, then approximately whole of August, and then half of this month that is May, and so there's not really much time. especially those who want to. I mean, obviously, everyone here wants to partake in this year's recruiting. Approximately 2.5 solid months to just do something for yourself, which isn't like little in my experience. Um, like in my experience, I entered the summer like this month. I entered ending of May without knowing data structures and algorithms, without knowing any of these things you people know, without knowing stacks, queues, linked lists, any of those things. But by God's grace, I was able to put in the effort and everything, cover all those things in time, while doing an internship and while also attending some class. Like it was a whole bunch of something while also having an almost close to empty resume. So like I had to juggle four things together. I mean, it was very difficult. Time wise, I had to invest lots of time, but it was definitely doable, right? But some of you are already in very good shape. You know data structures and algorithm to some extent. Even if you don't, through this workshop, you get to know more. Some of you have, one or two work experiences already. Some of you have a couple of projects. So I would say there's really no excuse anyone can give, like that most of you can give. But in the same vein, I feel like I understood that I was behind. I accepted that I had a lot to do, right? A lot to catch up on. And I didn't want to give myself the excuse of, oh, I came to school, wanted to go to medical school. I wasn't a computer science student. So if I get nothing this year, like there's nothing, I don't want to give myself the excuse. Like, you can always give excuses. But I'm like, if this my friend who's been doing CS since they were born can get something, then I can equally get it, right? So oh shoot, I was muted and I was talking. Huh? Okay, okay. Let's try again. Yeah, I'll do the talking at the end of the thing. Good. So, but then can anyone hear me? Can everyone hear me? Can everyone hear me? But can someone talk? I want to hear from your ends and see how it is.
Hi,
Yeah,
hi,
we
hi.
can hear. Hello.
Yeah. Okay, I think I can hear you both clearly. Okay, so let's
Okay.
okay. I think it's clearer now, right? Wait, is it clearer now?
Yes, it is.
Yeah.
Yeah, it is.
Okay, okay, then let's do it then. Okay. So let's just do quickly and we will actually finish this in time. Okay, so today we just want to complete our binary search and binary search trees, and then we go to heaps and priority queues, and then we are done. Okay, so we already started binary search trees, and we said binary search trees are simply binary trees with an invariant, right? And we said invariant simply describes like some restrictions or some things that always hold true, right? For some method, for some data structure or something. So for the binary search tree, if you have a tree like this, right? If you have a tree like this, right, for a particular node, all nodes that are to its left must have value that is less than it, right? That means that if I take this node right here, all nodes that are to its left should have value less than that, right? If I take this node here, all nodes that are to its left must also have value less than it. In the same vein, if go to the right side, all nodes to its right, should have value greater than it. And that is what we described as a binary search tree. So if I have 4 here, right, 5 cannot be here. That will break the invariance. Why? Because 5 is to the left of 4, but 5 is bigger than 4. So this is not correct. In the same way, I can't have 2 or anything less than 4 here, right? And we say that this invariance must hold true throughout the tree structure, right? So that means that you don't have to check only for this first part. You have to likewise consider this as a tree, you have to consider this also as a tree and check and make sure that it holds here. Consider this as a tree, make sure that it holds here, right? So that's the binary search tree invariant, that the condition must hold throughout the tree. Then we talked about the fact that if a tree is complete, right? If it's complete, we also talk about balance, right? So if these two things hold, I mean, you can even just focus on the balance tree. I say balance tree. So let me change this color and let's put this here. So we know that if you want to search for a value in a binary search tree, you take log n steps, right? Expected log n steps. And what is log n steps? Here, n refers to the number of nodes in your tree. So you have 1, 2, 3, 4, 5, 6, 7, right? We have 7 nodes here, right? So let's just call it n is equal to 7, right? But then let's see how many levels there are in the tree. How many levels? So we have 1 level here, we have 2 levels here, we have 3 levels here, right? So a number of levels is also equal to 3, right? So we have 3 levels and 7 nodes. Now let's assume we are searching for some number, right? Let's assume we are searching for some number here. So let's just use this color. Why am I in? So let's assume we are searching for some number here. So ideally what we do is that we start at the root node, right? And be like, hey, I'm looking for this number. Are you bigger or smaller than it, right? If you are smaller, then we will just move here, right? And come here. Then you're like, hey, are you bigger or smaller than it? You're like, I'm bigger, right? Then we end up moving here, right? So that is how searching is done in a binary search tree. Because of the invariance, actually, let's use a more clear example. Let's, make this tree better. Let's fill it with actual values. So let's put maybe 8 here. Let's put, say 6 here. Let's put 5 here. Let's put 4 here. Let's put like 13 here. Let's put 13 here. Let's put 10 here. Let's put 15 here, right? Let's assume that we are searching for, what, this thing has been so messed up. Okay, so let's assume we are searching for the number 4. Oops, it can't be 4. Let's say we are searching for 7. It can be 7, but it can't be 4. So let's assume we are searching for 7. So this is how you're going to search for 7. We stand at 8 here. Always you have access to only the root node, right? The root node is what you have access to. You're like 8. Are you equal to, we are looking for this 7, right? You're like 8. Are you equal to 7? No, right? But are you greater or less than 7? 8 is like, I'm bigger than 7. If 8 is bigger than 7, that means that 7 must be in the left subtree, right? So then we will have to come to the left subtree. Then we meet 6. 6, are you equal to 7? 6 is like, no, I'm not equal to 7. Are you bigger or smaller? It's like, I'm smaller. That means 7 is bigger, so 7 must be on the right subtree, right? And then you end up coming here. So you see that you made 3 steps, right? 3 steps. This was 1 step, right? 1 step, right? Then 1 step, and then 1 step, right? You went down at most 3, you go down at most 3 times. That is equal to the number of levels, right? Does this make sense to everyone? The number of steps we take, you take at most log n steps. Let's discuss what log n means. So we already defined n to be the number of nodes, the number of items, right? So n is equal to 7, so log 7. Log in computer science is usually to the base 2. So it's actually log to the base 2 of 7, right? Log to the base 2 of 7. And this is approximately 3. Give me a second. Julian is calling. But okay. So this is approximately 3, right? Because 2 to the 3 is equal to 8, right? 2 to the 3 is equal to 8. So this is upper bounded, right? This is basically what I mean, right? So it's approximately this. So this is the condition, this is the situation that holds if I have a binary search tree. If we're doing like for an array, right? If you're doing for an array and you wanted to find, let's say 7, you'd have had to search every single thing here. You'd have had to go through every single thing here. That is linear search. But because of the invariance of the binary search tree, at each point we cut away about half of the tree data structure. So here, when we compared 7 to 8, we ignored everything here, right? We ignored half of it. That's just like how binary search works, which we discussed about a month ago, right? So because of this functionality, we say searching in a binary search tree is log n, right? It's log n. That means at each point, you ignore about half of the tree structure. When you got here to, you ignored half of it, and then you considered the other half. But we explained last week that this is not always the case, right? That it is possible to have a binary search tree and you still do n steps instead of log n steps. So n steps is worse than log n, right? And I hope that's something we all agree with here, because if you have n is equal to 8, right, log n is equal to 3. I said the log is to the base 2, right? So does this make sense to everyone? That if you have a binary search tree that looks like this, you're going to take log n steps to do searching. Does this make sense? Does this make sense to everyone?
Yes.
Okay, now let's go to the bad case. But then we said a binary search tree is simply a binary tree with the invariant. And what is our invariant with our condition? A condition is that for every node, right, all nodes to its left must have value less than it, but all nodes to its right must have value that are bigger than it, right? But then let's consider this binary search tree, which we drew the last time. So we said you can have this, right? 1, 2, 3, 4, 5. Is this a binary search tree? Anyone? Is this a binary search tree? Yes or no? Is this a binary search tree?
Yes, it is.
It's a binary search
Yeah,
tree, right? Because if we take 1, all nodes to its left are bigger than it. If we take 2, all nodes to its right, its right, are all bigger than its right. So the invariant holds. So now let's try to look for 4. Let's try to look for 4. So let's say 4 is our target, right? 4 is our target. So if 4 is our target, we start at the root node. Are you 4? No. Is 4 bigger than you? Yes. Are you 4? No. Are you 4? No. You end up, doing you end up traversing or considering every single node. So this searching takes n steps, right? Which is worse than the log n we had here, right? And that brings us to the next case, which we also discussed about balanced binary search trees. So this construction is very bad, right? We don't want a construction like this. But if you have a construction like this, it's not any better than your normal array or your linked list, right? So you can convert this guy to a balanced binary search tree, right? And let's see one way we can actually construct that. So one way you can easily do that is you can actually take 3. Let's take this 3 here, right? We can take this 3, then we can make 3 the root node, then we can put maybe 2 here, right? Then we can put 1 here, then we can maybe put 4 here, then maybe put 5 here. Somebody will be like, I think I can also do better. So maybe we can make 4 the root node, then we can maybe put 3 here, then maybe we can put then we put 2 here, then we can put 3 here, then we can put 1 here, then we can also put 5 here, right? So can you see how here we have reduced it from how many levels were here? Here there was one level. So 1, 2, 3, 4, 5, 5 levels. We have reduced everything down to 3 levels, right? So that is also one thing you should keep in mind, that if your tree structure is not as good as this, you're going to always do bad, just like you are dealing with an array or a linked list. Does this make sense to everyone? The concept of balanced binary search trees. Does this make sense?
Yes.
Okay, so if you're in an interview and someone asks you a question that's not even just an interview, like in normal life, that searching in a binary search tree is always log n, the answer is false, right? Because it depends on the structure of the binary search tree. If it's as bad as this is wrong. But if it's as good as this, that is right. So that, computer science has this whole field where people try to, find the best way of constructing a good and a balanced binary search tree like this, giving some inputs, right? Giving some inputs. So maybe you have like the input coming in as a data stream. A data stream is like continuous data, right? Maybe 1, 2, 3, say maybe 6, maybe 0, 8, 9, 10. Then the question in computer science is, okay, how can I take this continuous data stream and construct an efficient binary search tree with it, right? And there have been many algorithms out there. We have the red-black trees. One is the red-black tree. Another one is the AVL tree. There's actually a couple more, but the most popular one usually is a red-black tree. I think Java or another programming language actually, we will do functional programming later on, and we touch on these ones also. So red-black tree is something you probably just want to look up. It's not that bad. Red-black tree simply tells you that a red node cannot have, we'll get to that later. But this is just something you should know, that the structure of the tree really matters. So that actually wraps up on a binary search tree, which we also did last week. And in the assignments that we gave, there was this question about validating binary search tree, right? So to validate a binary search tree, we simply want you to check if the invariant holds. And what is the invariant? That is, if you take a node here, right? Every node to its left should actually be less than it. Every node to its right should be less than it. And that's actually a very simple problem. So that's like, so assuming I have my function, the validate, and you have a node, right? So all you can simply do is that, well, we can first check if it has no children, right? So if not, right, node.left and not node.right, that's like if it's just like one single node, you can return true, right? If it's your base case. But node.right, then you can simply return true. This one thing we can do. Then the other thing we can do is that, now, please listen to this part carefully. Now, we've done recursion. We've solve examples on applying recursion to like linked lists and applying recursion to like arrays. And last week we did one question on applying recursion to a binary tree. But I want to show you, another way of applying recursion to a binary tree. So usually what I do is when I get a question on binary trees where I have to apply recursion to, most of the questions actually require recursion. I'll say draw a 3-node tree structure like this, right? Just draw a 3-node tree structure. The example may be very big and anything, but you try to restrict the problem to a 3-node tree structure like this. And ask yourself, if this is my binary search tree, how will I validate it? How will I solve the problem on these 3-node, binary search trees? So I'm like, okay, if I have this, something like this, what I'm going to do is that I'm going to take, so let's just put in some values. Let's say we have 3, then we have, let's say 2, then we have, say 5, right? Then someone is like, okay, what I'm going to do is that I'm going to compare, right? I'm going to compare. So currently node is 3, right? This is node. So if node, right? If node dot left, right? If node dot left, right? If it's greater than or equal to node, dot val, right? We know it's a node, right? And a node has a value. So if node dot left dot val is greater than or equal to node dot val, we can return false, right? Return false, right? Because this is node, right? This is node. If the left value is greater than 8, we can return false, right? That means that it is not correct, right? It's not a valid binary tree, right? Then we do the same thing for the right one. If node dot right dot val, if that is also less than or equal to node dot val, again return false, right? Return false, right? Return false. So this is what we are doing now. So we are like, okay, take the node, compare it to its left. If the left is bigger than 8, return false, right? Because that's not true. We want the left to be smaller than 8, right? Then take the right also and compare it to it, right? Like return false, right? We're like, okay, if these two conditions hold, right? If these two conditions hold, what must we do next? Then we go down, right? So as we did here, right? As we did here, right? If these conditions hold, then we can actually, go down to, check for the other ones, right? And that is actually it. There's one last trick I'd have to push in, but before I push in that trick, it's actually one last trick I'll push in. Before I push in that trick, you just follow me carefully. So then the other thing also is that we're like, okay, now let's validate, right? Let's validate our node, right? Now I want to validate node.left. Please follow me carefully. This is actually a very tricky question. It's not that simple, but follow me carefully. Let's validate node.left, right? And let's also validate node.right. Does everyone get me up to this point? Does everyone get this, like this temporary code we have written? Does everyone get it? Does this make sense to everyone?
Yeah.
If you're confused, even the slightest on this, please let me know. Even the slightest on this. Before we go on to the next thing, does this make sense to everyone? Okay.
Yes.
Okay, good. Now, the next thing I want you to keep in mind, I mean, the other checks we can actually throw in, right? The other checks are like if node.left, and in other words, we are making sure that there's indeed a node.left, right? Because if node.left is none and you try to access .val, it's going to give you an error, as we discussed last week, right? That our node structure is something like this: class node. It has a val and it has a next, right? For it to have, if this is none, right, .val is going to give you an error, as we discussed last week, right? And you can do the same check here, right? Now let's look at the next issue. The next issue we must solve. That's, I think, something people usually leave behind, is that the invariant must propagate throughout the tree. What do I mean? I mean that if I take this guy here, right? If I take this 5 here, let's undo, right? If 5, let's assume 5 also has, 4 here, and let's say 6 here. Let's just assume, right? What we are going to do is that when it comes to this 5 here, right? This 5, right, must also be less than this 8, right? You don't compare 5 to only 6, right? You don't compare 5 to only 6. You compare 5 also to 8. Does that make sense to everyone? Does everyone agree with this? That the invariant must hold. So far as 5 is on the left of 8, 5 must be smaller than everything that is here, right? 5 must be smaller than everything that is here and everything that is here. Does this make sense to everyone? Do we agree?
Yeah.
Good. And because of that,
Yes.
one way to do that is by doing this. that at each point, right, that at each point like this, let's use this, at each point like this, right, let's assume this is a tree structure. At each point, what we are going to do is that at each node, we are going to track the minimum value and the maximum value that is there, right? So at the root node, we can set the minimum value to be minus infinity. That is like the least value, possible. And at the maximum value, we can set it to be positive infinity at the root node, right? When we go down its left subtree, please follow me carefully. When we go down its left subtree here, right, its left here, we know that this left here, right, this left here, can we all see this left of circled here? Can we all see this? It's a bit,
Yeah,
follow me.
yeah.
Like this, like one of those things, like you should know. I think it's really good to know. Like last week, we did a very simple one where you want to know the length of the tree, or you just like find the length of the subtree, just 1 plus this. But it's like a typical binary search tree question where you add your own inputs, like we are doing here. Okay, let's proceed. Let's use a different color. So, okay. So now, once we go here to this guy, right? Once we go here to this left subtree, we know that its maximum value is bounded by this guy, right? Like this value here cannot be bigger than this value here. I hope we all agree that that's the invariance, right? Because hey, you're to my left, so you should not be bigger than me, right? You cannot be bigger than me. So when it comes to this guy, so let's call it node 2, right? So this is node 1, node 1. So if you come to node 2, so at node 1, this was its minimum, this was its maximum. When it comes to node 2, right, its minimum can still be minus infinity, but its maximum changes, and its maximum becomes node 1 here, right? And its value cannot go above that, cannot go beyond that. Do you agree with this? Do we agree with this? Does this make sense?
Yes. Yes.
Okay,
Yes,
good.
it does.
Now let's go on. Let's go on to say, now let's say we are on this node now. Let's come to this node here. When we come to this node also has very interesting situations here, right? So what I'm just trying to say is that as you go down, this min and this max value is actually going to get updated, right? For each recursive call, right? So if you get to each node, you have to compare it to the minimum value that it can be to the maximum value that also upper bounds it, right? So let's say we get to this value here. Let's see if we can get the maximum value this guy can be. What do you think is the maximum value this guy can be? This guy here. What do you think is the maximum value that it can be? So let's say this is, you can call this node 1. Let's make it clearer. You can call this node 2. You can call this node 3. You can call this node 4. You can call this node 5, node 6, node 7, node 8, and node 9. Which of these nodes do you think bounds the let's start with minimum, let's start with maximum value. Which node do you think bounds the value for node 4? Which node? Which node do you think here bounds it? Or if it's infinity, to just tell us infinity. Which node here? In other words, which node do you think node 4's value cannot go beyond? Node 4's value cannot go beyond. Anyone?
It shouldn't go beyond the first one.
Which one? Node what?
Node 1.
Good, exactly. It can't go
Node
beyond
2.
node 1. Right. Now let's take node 2. Can it go beyond node 2? Can node 4's
Yeah,
value be bigger than node 2?
yeah, it can.
Yeah, it can be bigger than it, right?
Yeah.
Because node 4 is to the right of node 2. Right? Node 4 is to the right of node 2, but it can't go beyond the value of node 1. Why? Because it is to the left of node 1, right? So
Yeah.
if we take only, if we take node 4, right, its maximum value is bounded by node 1 again, right? Because node 1, it is to, what do you call it? It is to the left of node 1. I hope this makes sense to everyone. Is it tricky? But like, does it make sense? What I'm trying to just tell you that because people make this mistake where when they're validating a binary search tree, they only compare the node, right? Like the node to its parent, right? They just compare the immediate, they just compare the immediate structure. But I'll give you a wrong answer because the property, the invariance must hold throughout the data structure, right? It must be true throughout. So you must keep track of your min and your max. Does this make sense to everyone?
It makes sense.
Good. And this was in the week's problems. I don't know if you were able to go through it, but I just wanted to touch on it today. And that is something you should know. Okay, so that's all for binary search trees. And I think we've actually gone through like a lot. The other algorithm I would say you should go through, I think we can actually just mention that real quickly, is deletion. I think that is actually the most involved algorithm in binary search tree, so deletion. But we can just go over the algorithm briefly. If you get delete from a node in a binary search tree in an interview, I think that's probably the only question you do. If you only give you like, unless you're a very fast programmer and you can finish that like very much in time. So it's actually a very a very fun thing. When I actually learned this thing, I actually wrote out the algorithm, which was very involving, honestly. So let's say we have 10 here, we have 8 here, we have 4 here, we have 9 here. My budgeting was wrong. Okay, let's put 8 here, then let's put 7 here, let's put 9 here, let's put 14 here, let's put 12 here, and let's put 16 here. Okay, so let's assume you want to delete node. Let's assume you want to delete node 9. What do? We just traverse, right? We can just traverse here, come here, just delete node 9. Do you agree that that's how we delete node 9? Does it make sense to everyone? Just start at 10, come here, come here, come here. You can easily delete node 9, right? Let's assume we want to delete node 8. Right? Let's assume you want to please follow me carefully. If I want to delete node 8, I'll start at node 10. Then I'm like, 8 is less than you, so I come here. 8 is bigger than you, then I'll come here. When I delete node 8, what do? Node 8 is a parent to some nodes, right? In fact, let's even make this, let's make this even like this. So if I delete node 8, what happens? Node 8 has a child 7. So what do you think we should do? Anyone, what do you think we should do? We want to delete node 8. But if you just delete node 8, it's going to leave a child hanging. So what do we do? Let me check the chat. If someone's saying something, you can type it in the chat or anything. Like, there's no wrong answer here. If I delete node 8 right now, we all know node 7 is going to be left, right, as an orphan, but you want it to still be connected to the family tree. So, I mean, logically, that's like just put 7 at where 8 is, right? So we end up getting something like this, right? You put 7 here, right? That is perfect. It's very perfect, right? Actually, this is it. Like, if you delete a node that has just one child, it's simple. Just take that child and fix it in there. But it becomes tricky if the node has more than one child, right? So let's go to that case. So let's assume we have this one. We have this one here. If we delete 8, right? What do you think we can do if we delete 8? Anyone? What do you think we should do if we delete 8?
Yeah, I
It's
think
not
one way
tricky.
that we can do is like after doing the swap, or like after assigning the right value of 6 to, let's say, any value, either the left or right, the right of 8, then we try to make sure that we are maintaining the invariant by maybe reordering it. I don't know, but
Okay. So you are saying we can just use any of these and push it here, then we can just try to fix the tree underneath, right?
yeah,
Okay.
yeah,
I mean that's definitely a good thing, which actually may sound tricky. So let me extend this tree structure. So now assume this has a node here, this has a node here. So assuming 9 has maybe 8.5 here, and 9 has, let's say, 9.5 here, right? So ideally, what we usually do, let's just go over this quickly. What we do is that, I hope I remember this, was about 2 years ago. If you stand here, you move here, you want to delete 8. What you do is that you find what you call the successor node. The successor node. What is the successor node? Right? As in, like, succeed me. Successor node. This is how you usually find the successor node. When you go to the 8, right, move down 1, go to its right by 1, right? Then move left till you hit the last left node. So here is 8.5. Take that node and come replace it as a new successor. And you are done. You don't move any other thing. You are literally done, right? Now let's see. If I'm here, right? If I'm here, 8 is what I want to delete, right? But we said 8 has 2 children. If it had 1 child, it's simple. Just move that child up to replace, the parent. But here, it has 2 children. So what you do is that go right by 1, go right by 1, right? Just move right by 1. Then when you are there, now on that one you are on, that's a right child, go left till you meet that left child, right? And here it is 8.5. So let's take 8.5. Then they said, okay, now take that one and bring that one here, right? So now this becomes 8.5, right? Then we will delete this 8.51. We have already discussed how if you're deleting a leaf, you can just delete it and you're done, right? So deleting this is very simple, right? Now, can you see that? Is the tree a balance? Is it a valid binary search tree? Anyone? Is this tree a valid binary search tree?
yeah, it is.
Yeah, it is, and it's balanced. We are done with the
Yes.
deletion. Like it's so perfect, right? Like it's a very beautiful algorithm. Like this is definitely not the only way. Like as Jeff has suggested, you can actually do that, but that's going to cost you a lot. But this one is
Yeah.
so pretty. You just have to the node you want to delete. If it has two children, the algorithm is to simply go right, get to that one node, then go left, 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 left till you find the successor node. That is simply the leftmost node. And what do? Just take that leftmost node's value, right? And just take and just bring that one up here, and you're done. And then your resulting tree is a valid binary
Yeah.
search
I
tree.
have a question.
Yeah.
So, like, how do you know that this is the successor node?
Yeah, so the successor node to find good. So to find a successor node, right? To find a successor node, the algorithm is to simply, right, go right. So let's break it down. So we first broke it down into so we first had a node that was a leaf node, right? A leaf node. That's like it's like it has no child, right? Then we had a node that has one child, right? So it could be a left child or a right child, right? Then we had a node, right, that has two children, right? Then finally we had a node,
Mhm.
right, that has two children, and there are like a bunch of stuff under it, right? So if you delete this first guy, it's gone, right? A leaf node, we don't care about you. Like you're already lonely, right? Just go. If you delete any of these guys, right, just push any of these up, right? That'll work. If you delete this guy, right, ideally just move right like this, right? Then you move left. But you see, moving left, there's nothing there, so you can actually bring this up. Actually, you can even bring this up, and it will also work, right? But in a case like this, to find a successor node, the algorithm is to simply move right once, then move left throughout. Move right once, then go left, 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 and you are done. Right. So that's how I find the successor node.
Mm.
Move right once, then go left, 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 left. Now, assuming it was even like this, if you had this, right, still, this would have been the successor. The moment you move right once, you don't move right again. Move right once and just go left, 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 and you're done. Does this make sense?
Yeah, it makes sense. So, like, you move after moving right once, you move to the left until you get to where, like, there is no subtree on the left,
Yeah,
right?
exactly. And then you pick that one and then you
Okay.
bring it up. I would have actually, show you the code after we're done, but I want us to go to the next data structure. So please, these things about the binary search trees are so crucial. They're very important. And I would say make time to really go through them, solve a few problems, and you should be very good. If you get a question like this in an interview, you should be very glad because honestly, it's not the easiest. When I took a data structures and
Okay,
algorithms,
so I have a question.
yeah.
So what if there is no right?
If there is no, okay, yeah, good, 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 good. If there's no right, that's like the tree has just one child. If there's no right, that means you're in this situation. That means you're in a situation like this, right?
No, I'm talking about
Mhm.
there are multiple nodes, but the node we want to delete has no right child.
Yeah. So if that's no right child, that's like you're in a case like this, right?
Yeah.
Yeah, and that's the same as this. And we said in a case like this, you can simply, where's the red? You can simply delete this guy and just move the child up. So here, I'll delete you and I just move this guy up. Like I just shift the tree up by one. Does
Oh,
this make
okay.
sense? Yeah. So if like there's just one child, just delete the node and just move the subtree up by one, right?
Okay. Okay.
Yeah.
Hello, please.
Yeah.
I wanted to ask what's the name of this algorithm?
I read it from a book. That just says deleting node from a binary search tree. Let me actually show you something. Let me try and open. No, not this. Let me try and open. Can everyone see my desktop?
Yes.
So this is the okay, this is the notes I took when I was learning data structures and algorithms in like 2021 or something. We are doing binary search trees, right?
Yeah.
Let me see. Maybe I search for successor node. Wait. Um, wait. Graphs, binary search tree. No, not this. Okay, I don't know how easily I can. I don't know. Sometimes this thing even confuses me. With code, graphs, hash tables, is anagram, OOP, node based structures. Class node, insert node, delete node. I think this linked list. Wait, I want to show you. I wanted to show you the code I wrote some time ago when I was learning this guy. Okay. Okay, looks like I can't easily find. Oh yeah, binary search trees. Good. Search node. Good. So this is the algorithm. Good. Yeah. So to delete a node, what did I do? See, I even skipped that code. I was scared of it at that time. I wrote else pass. That means I didn't even implement it, but I can actually implement it now. So if you want to delete a node, right? If elif value is less than node.val, you just do this. This like if it has just one child, if it has like blah blah blah, then here is if it has this and that, then if it has only like if not node.left and node.right, that means if it has, let me enlarge this for everyone to see well. So this like if it has no left child, right, but that's a right child, what do? I just return node.right child, right? That's like just move the right child up. In the other way, if it has no right child but has a left child, just move the left one up. Else, this else case is there. So it's a node 1. So else I'll do like this. Else I'll be like, okay, so let's take the right node, right? Else I'll be like, okay, let's actually write a function and say find successor. Let's say we have successor, right? Let's create a function called find successor node. And we're going to pass a node to it, right? Then let's implement find successor here. We can actually put it inside this function like this, def find successor. If you put a function inside another function, we can actually call them inner functions. Then how do you say we find the successor node? How do you find successor node? Just go right once, right? So we go right once, right? Then what do? We go left, right? So let's just call it n, right? We go right once, then we'll be like while n, right? While n simply means that while n is a node, right? While n is a node. Or we can also do while n dot left, right? Then we'll be like n is equal to n dot left. This is like the whole thing. So by the time it breaks out, n will be the leftmost node, right? N will be the leftmost node. Does this make sense to everyone? So here we are like, okay, the tree structure is something like this, right? It's something like this, like 4, like say 1, say 2, say 1, say let's go like 3, like say 1. So we are like, for you, what do I want to delete? Come right once. That's what we do here. Then what do? Go left inside the while loop, go left inside the while loop, and here n2 has no left child, right? So the loop will break, and then it will be at 2. And after you're done, we can actually just return n, right? So when this guy returns the n, right, then this guy returns the n, what we do now is that we change the current node's value. So here it's 4. We're now set its value to 2. So we do something like this: node.val is equal to successor.val, right? Then what do? Now we don't need these 2 anymore. We need to delete these 2. Right? We need to delete these 2. And then we call the delete node method that we are now implementing, this delete node method, on the successor. And then you're done. Then at the end, you return node. That's literally all. Exciting, right? Yeah, it will be in this week's practice problems, so you have more fun with it. Let's go to the next thing. We're actually behind on time, and then we will finish. Heaps and priority queues are actually like very closely related to trees, so I think it will be relatively quicker to just go through them. Okay. Yeah. Wait, it's everyone. Does it make sense to everyone? Is it going well with everyone, or is it a lot? But at least, like, do people understand the algorithm?
Yeah, we understand it.
Yeah, we do.
Okay, good. Let's go to, when I had an interview last 2 months, actually with Amazon, my final interview, the interviewer was like, what's your favorite data structure? And I was like the priority queue, right? That is the structure we actually come to discuss. Priority queue. A more fancy implementation of this is the heap. So he was like, okay, tell me about it. And this the analogy I use. So assuming you go to a hospital, right? And in a hospital, when there's an emergency, right? In the hospital, it's not first in, first out. In other words, it's not first come, first served, right? The hospital is not like that. when many people come to the hospital, we take the one whose situation is right, is very urgent, right? I think an accident happened. Everybody's rushing someone in. We take the person who is like who has lost like the kidney, 4 eyes, all their 2 eyes, and their limbs and everything. That is more urgent, right? That's how the priority queue data structure works. You may have data, but to each data we associate a priority, right? An importance. And then we will serve the request. In other words, we will, give you or attend to the point or the data point that has the greatest priority. That is basically how the priority queue data structure works, right? So it's not like the stack, it's not like the queue, it simply deals with priority. Which one do you attach much importance to, right? And yeah, we had a very nice discussion, and thankfully the man liked it. Okay, so let's go to the priority queue data structure. So as we said, it's like this, just like a queue, like as we already said, queue. A queue is first in, first out, right? That's how a queue data structure works. So, but we said for a priority queue, it's not necessarily first in, first out. Rather, we care about the importance. So there are many ways to implement a priority queue. So assuming your data point comes this way, there's, let's say, a name of a person. So let's say A, then their priority 5. Then maybe there's another person B, then their priority 6, right? Then maybe there's C, then priority 7, right? So assuming this is your data point. So ideally somebody will be like, I can use a normal queue, I'll use an array. Then after that, I'll sort based on the priority, right? And then I'll give you the information. That is indeed true, right? Like you can just sort it based on the priority, right? And then you give it to me. But sorting is n log n. Right? Sorting is n log n. So as usual, computer science and their questions, can we do better? Can we do better than having to sort? Because it's actually, I mean, if you insert a new element, what do you do? If you insert a new element, that means you have to go and resort again, right? To make sure you maintain the structure. But computer science, as usual, wanted to do better. And that is when they came up with the idea of the heap, right? So let's see how the heap is. So don't forget the whole thing we want to solve. The whole thing is that we want to create a certain data structure, right? That will enable us to get the item with the greatest priority first. So here, if we're getting an item, it will be C, right? In other words, if we put this whole thing in a data structure and we want to get an item, it will first give us C. Why? Because C has the greatest priority. Then it would give us B, because B has the next greatest priority. Then it would lastly give us A, right? So that's the data structure they wanted to create. A data structure that will give you the item with the greatest priority first, right? So we first discussed what if we use a normal array, right? Where we sort based on the priority, right? Because that way it will be easier to obtain it. But we said that is n log n, which is sorting, which is bad. So we want to do better. And the next better thing they proposed that we do is to use the heap, right? The heap. And the heap is so pretty, like the heap is so good. So let's see how we can use the heap. So this is how the heap works. The heap is just a tree. Heaps are trees, right? Very, very nice trees like this. And what the heap does is that, okay, as for me, the item with the greatest priority should be at my root node. That is all I care about, right? That is the invariant for the heap. He says like, that's all I care about. That the item with the greatest value should simply come up here. Every other thing here, I don't care about it, right? Every other thing I don't care about. So for that, it maintains its invariance mainly at the root node, right? So if you put these things in a heap, instead of put C here, right? Then I'll put maybe B here or A here. It does not matter, right? So I'll put them there. That is how the heap works, right? Now let's talk about the next thing about the heap. The tree that represents a heap must be complete. What do you mean by the tree is complete? I hope that's the right word I'm using. Well, the tree is complete if there is no holes to the, let me make my math well. Blah, blah. See, let me just explain to you what I mean. You get it. Okay. So let me draw a couple of trees here. Okay, so look at these trees. This tree is complete. Why is it complete? It's complete because, okay, this tree is not complete. It's not complete. This tree is also not complete, right? Now, why do we say so? If I take this tree, right, if I take this second tree, if I take this second tree 2, you can see that to the left of this guy, there's a hole here, right? There's a hole here. I could have put something here. And because of that, we say this is not a complete tree. In the same way, if I take this guy here, if I take this third tree number 3, there's a hole here, right? To the right, to the left of this guy, and there's also a hole here, right? So it is not complete. But if I take this guy here, like there's no hole, right? When you go here, you see a node there, right? That is why we call a complete tree. So the heap requires that your tree is complete. That is, you have no holes inside the tree structure. Does this make sense to everyone? I don't know if you got it.
Yeah.
Does this make sense? It makes sense, right?
Yeah, it makes
Yes, it
sense.
makes sense.
Okay,
Yes.
good. Yeah. My English had to be on point, even though it wasn't about. You don't even need to even remember the technical terms. Just, nobody's going to, bro, people don't remember technical terms. Just be like, there's no node to the right of it. There should not be any hollow space, whatever, and you are safe. Okay, so that is one thing you must remember. So the two things we've discussed about the heap data structure is that one, the item at the root node has the greatest priority, right? And then you also want to, maintain this guy here, right? That you don't have some hollow things to the left of it, right? So let's go to the next thing. There are two types of heaps. You have the main heap and the max heap. So what does the main heap do? So look at the example we gave here. So the example we gave here, we said A has priority 5, B has a number 6, C has a number 7. The main heap would put A on top, right? That one is kind of like the minimum one should be on top, right? So this is a main heap. So a main heap would have had a main heap would have constructed this as this. So to put A here, then I said B and C doesn't care where it puts them, right? So this is a main heap. And a max heap would put the one with the greatest value on top, right? That's basically the difference between them, a main heap and a max heap. Is main heap and max heap, is it okay with everyone? Does this make sense? Like the main heap will put the smaller value as the root node, and the max heap would put the bigger value at the root node. Makes sense, right?
Yeah, it makes sense.
Good.
Yeah.
In Python gives you a way to just, so for Python, you can actually import heap kill. I don't know why they call it this way, but heap kill, right? Heap kill. And this heap kill you are importing automatically comes with a main heap, right? So assume you have an array of numbers like this, a list of numbers, list 2, 8, 1, 4, 5. In order to construct a main heap with this, all you need to do is to just do heap kill. See why I like Python? The heapify nums, right? This is all you need to do, and you are done, right? In Python, by doing this, you have actually created a heap from this, and it does it in place. So you construct something like this. I think 1 will be on top here. You put 2 here, then maybe 4. Then put like 5 here. Then put like 8 here. As I said, 8 could have been here anyway. It doesn't matter. All it cares about is that you maintain this invariant at the top, right? That is actually what matters, and it does it in place, right? Please don't assign this to nums. This is not going to work, right? So what you do is that, that's a mistake people usually make. What you do is that first create, your list like this. First create it like this. It doesn't even have to. It can be just any iterable, right? I think so. Just first create it like this, and then just heapify it, right? Heap the heapify nums. Then it will create the heap data structure for you, right? If you want to remove the topmost item, all you do is that you do heap q dot heap pop. Yeah, I know the names are nice. But heap pop, I think it's double P. Yeah, heap pop, then puts nums in again, and this is going to return to you 1, right? As the topmost item. And as I said, this normal heap queue, right, is actually a main heap. The one in Python, if you import heap queue, is actually a main heap. Now, how do you think we can convert this to a max heap? Anyone, any ideas? How do you think we can convert this to a max heap? So we said the normal one Python gives you when you do import heap queue is a main heap. So how do you think we can convert it to max? So assume the heap we want, right, is such that 8 is on top because 8 has the biggest value, right? So this 8 has the biggest value. So we want 8 to be on top and we want the rest of the numbers to be under it. So how do you think we can convert a main heap to a max heap? Anyone? Anyone? You can put in the chat just any ideas. I think you can do it. Good. That's the answer. Just negate it. You just negate it, right? That is all you do. So you just negate every single thing, because if you negate it, which one becomes the smallest now? 8. 8 becomes the champion now. And to put minus 8 here. So all you do is that when you pop out, just negate what you get. And that is the trick people use. That just negate every entity, right? And then you then use your normal, the what Python gives you. Python, because the biggest will now become the smallest. And when you pop out, just negate the value you get. And then you are done. And that's basically it. There's another, so Python automatically gives you a heap. Python also gives you a priority queue. I failed to mention that. So if you also want to use a priority queue in Python, you can also automatically import it. This is how you import it. You do from from Q, if I'm not wrong, import. Please, if you're using Python 2, it becomes uppercase Q like this. But I hope nobody is using Python 2 because my ancestors don't see me use it now. Actually, if you're using MacBook, its default is Python 2. I guess it's my ancestors. Okay, so if you do this in Python, from Q, import priority Q, you also get a priority Q from Python free of charge. And what you do is that you like Q is equal to priority. For that one, you initialize it this way, right? Like you initialize it this way. So this is a priority queue, right? But if you want to use a heap, you first create the iterable and then you just heapify and then you are done. Last thing, if you want to push to the queue, to the heap, you do heap queue dot heap push. I think the first argument is what you want to push to your existing heap. Then the next one is a value, right? So let's say 10, and then it will push it inside it for you, and you are done. So cool. Yeah, Steven. Yeah, Richard can ask
Yeah,
it.
so does it only work on what do you call it, integers, or it works on strings?
So that is a very good question. So you realize that it's just a matter of comparison, right? Like the data structure just needs something to compare. So if what you're passing to it can be compared, right? So when we did about 4 weeks ago, we talked about the comparable, like comparables and iterables. If you do Java, you're more familiar with iterables and comparables, right? So like in Java, if you want to compare something, just make it implement the comparable interface. You want to be able to iterate over something, blah, 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 yes, blah, blah, blah. Yeah. So integers are easily to be compared, right? 2, 4, 5, 6. Like nobody needs to tell you which one is bigger than the other, right? It's easily comparable, right? Other data types are also comparable. But let's assume that's actually a problem I solved last week, that you want to talk about nodes, right? Now let's do this question. It's actually a very fun question I came across. There's lots of solutions, but please follow me. I know somebody said they hate linked list. Welcome out to linked list. Look at this question. Assume you have, let's just use 3 linked lists. I think that'll make our lives easier. Let's assume you have 3 linked lists, right? Please follow me because we're actually almost done. Like after this one, we're actually done. I know we have gone behind time. Okay, we're actually late. Okay, assume you have these linked lists, right? And each of these linked lists is actually sorted, right? So let's say 1, 2, 3, 4, 5. Let's say 2, 3, 7, 8. Let's say we have 4, 5, 6, right? Each of these linked lists is sorted, right? Does everyone get it? Everybody remembers what a linked list is, right? I hope so. Okay. Now let's say we want to merge all these into one long linked list. Anyone, how do you think we can do this? We want to merge these 3 linked lists into one. Anyone, any ideas? How do you think we can do it? Anyone? Maybe just 1 or 2 sentences works. Anyone? How do you think we can do this? What I'm going to explain is very, very key to know it. It's a feature very common in functional programming, but yeah, how do you think we can do this? Yeah, we can use pointers, right? Yeah, or one thing we can also do is that you can just take like the first 2, merge them, and take the result and merge it with this one, right? I didn't ask it. I hope everyone gets that. You can just take this first 2, so you can just implement some function that merges 2 lists, right? So like def merge 2, right? And then inside, so let's say list 1, comma list 2, just use 2 pointers to merge them, right? I hope everybody understands that one. Then their results, you then merge it with the third one, right? Is that okay with everyone? Does this solution sound good to everyone? Before I go to the one I want to show you.
Yeah.
Okay, good. Now let's go to how we are going to use a priority queue. That's so cool. Look at this solution. I don't know. I just get excited about certain things. I don't know. It's weird, but yeah. But look, it's very fun. Okay. Now we're going to create a priority queue, right? Somebody will also be like a heap. Don't worry. Basically the same thing. Okay. So this is what we're going to do. You know that you only have access to the root node, right? To the, you know, like linked list, you only have access to the head, right? So let's take all our what do you call it, our linked list, and put them inside our priority queue, right? So this is list 1, this is list 2, this is list 3, right? Put them all in list 1, list 2, list 3. Now you know that it is a min heap, right? So a min heap is just going to have them just as we have it now. Does everyone agree? A min heap will put it in like L1, L2, L3. We are doing it this way, like a min heap, like the first item, assume that the first item has the minimum priority, right? And here, the priority is like 1, 2, 3. Because for linked list, you only have access to the head, right? You only have access to the head. Does this make sense to everyone? Like, to put it in this way, L1, L2, L3, where L1 is like the least priority for a main heap. Is this convincing to everyone?
Yeah.
Yeah, so like L1 is standing on the head of this, L2 is standing here, L3 is standing here, right? And our main heap of our priority queue, we'll just do it exactly the same way, right? Because 1 is less than 2, that is less than 4, right? Then look at the cool thing we do. Then the cool thing we do is that we then pop out of our priority queue, or we get, when you get, it's going to give you the minimum one out, which is L1, right? So let's assume this is our result. Let's assume we are tracking our result here. Let's use a different color. Let's assume we are tracking our result here. Currently, it's just some dummy pointer, right? Some dummy node, right? It's waiting for the next node, right? So what we can do is that, okay, when we pop out of our priority queue, it's going to give us L1, right? Because L1 is currently standing on 1, which has a minimum value, right? Then we are like, okay, take that node, right, that it just gave you, and go and join it to this guy, right? So you're going to have that current L1 node here. Then let's move L1 to L1.next. So L1 becomes L1.next. So take L1 and move L1 forward to here to stand on node 2. That everyone get this second step I did. Does everyone get the second step? So what I simply did was that when I popped out of my queue, right? Now my queue, when I popped out, I just had these two things. I had L2 and L3, right? So I popped this one out, L1 out, and now L1 is here. And I'm like, okay, L1, you are the one I got. So that means that, you are the smallest. I just take your node, that first node, this node 1. Now I assign it to my, my result here. Then after that, I'll move L1 forward, right? Because it's links, right? So L1 is now standing here. Does this make sense to everyone?
Yes.
Good. Now the next thing I do is that, okay, now to your queue, let's call our queue uppercase Q. I'll be like, to the queue, add the new L1, add L1 again. So L1 now is standing on 2, right? Oops. L1 is standing on 2. So if you bring L1 again, right? If you try to, it can put it here again, L1, because this is where you are now. 2 is equal to 2, 4, right? So it's going to be, it can be like L2, L1, but like it doesn't matter because they're both 2, 2. Does this make sense? Does anyone know where the algorithm is going to?
Yeah, I see it.
Yeah.
Right? Then you do the same thing again. Then you pop out of your queue again. If you pop out of your queue, it's going to bring you L1 again, right? Then just, link it again, right? So here, L1 had the value 1, but now it's going to have value 2, right? Then you move L1 to the next one. So L1 now points to 3, right? Here. And then you push it to your queue again. But when you push it to your queue again, look at something. If you push it to your queue again, so when we pop it out, we have something like this. But when you push it to your queue again, it's no longer going to be here, right? Why? Because it's now standing on 3, but L2 is standing on 2, right? And the priority queue will adjust itself, and then it will put L2 first. So L1 will now come here, right? So next time, if you pop out of your queue, it's going to bring out L2, right? And then you take L2's node, that is this 2 here, right? And then it will fix that one as the next one. Can you see the pretty thing? Like, you just put everything in the queue, just pop out, remove the node, fix it, and then you're done. So cool, right? Looks like I was the only excited one. But yeah, it's really cool. It's really cool. Yeah, when I saw this algorithm, I'm like, bro, this is so cool. Good. Yeah, now let's come to the issue of comparison. But the thing is, linked lists have no default comparison, right? Like, they are linked lists, like they are nodes, right? I hope you all know they are nodes. Like, they are nodes, right? They're all nodes. We're coming to Steven.
Yes.
They're nodes, right? They just have value and next pointers. But someone is like, but then the Qt data structure can only store comparables. It needs a way to compare L2 to L1, right? Because it just sees them as linked lists. So what you do is that you give the node a superpower. How do you give nodes superpowers? This is very common, like in functional programming. So you can just write what we call them wrapper classes, wrapper. So class wrapper. So let's see what the wrapper class is going to do. Just, a normal class like def init, then it accepts, self is a normal thing, then it accepts a node. Then what does it do? It just sets self.node, like it's just your normal Python code, is equal to node. Then what you do is that you define a dunder method. The dunder method you define is __lt __ self. I'll explain this soon, don't worry, and other. These are just functions. Then just do return self.node.val is less than other.val. By doing this, you have given it superpowers. What are the superpowers you have given it? You can compare 1, 2, 3, which are normal numbers, right? But now you have given us a way to compare nodes, right? How did you do that? You're like, okay, now for every node, I'm going to convert it into a new object, right? for every node, I'm going to convert it into some new, some new, what do you call it? Some new data structure, right? What is that data structure? That is here, the wrapper, right? It's a wrapper class. So you're like, that wrapper class is going to take that node you have to just set it to be node. Then it applies, it gives it this superpower method called __LT, right? This LT simply means less than, right? Just take less than, and you're like, if you have this current node, that is the self, and any other node, so you want to compare this current node to any other node, how do you do it? Self.node is less than val, right? What did I just say? If self.node.val is less than the other node's value, then it is less than it, right? So less than, so this is like true. If self.node.val is less than other.val, then this current node is less than that, right? That is simply it. You can, if you don't want to even write a new wrapper class, all you can do is that when you write your class node, right? Class node, you can simply just add this thing. Like this is the thing perform the superpowers here. This less than is called danda method. Danda method because double underscore. So programmers just call it danda, right? Double underscores. So if ints already have this thing implemented, right? More life. Okay, yeah. So any class, right? Any class that has this underscore thing there can be what do you call it? Can be compared, right? So if your node class definition has this underscore thing, then you can compare it. Does that make sense? Richard, does it answer your question? That if you node, so like your class here, yeah. So if you just add, what do you call it? So if you have any class, if you write your own class and you think you'll be comparing your class, right? You'll be comparing your class, like you'll be comparing objects of your class, just add __LT__, then self, other. Other is like another node of its kind. So what you do is that if you want to write a lot of code, so if self.val is less than other.val, return true, right? So then it will know how to compare it, right? And that's all. That's literally everything you need. Does this make sense to everyone? I know we've gone through a lot, but like I hope.
So how do you use it in the code?
What did you say? Richard, can you repeat?
How do you actually use it in the code? Like how do you use the wrapper class in the code?
Oh, good. Let me show you. Give me a second to open a question that I solved recently on that. How do you use it in the code? Let me show you. Give me a second. My internet is like the second worst in the whole world. Wait, I'm just showing the last thing that we actually done. I'm trying to open the LeetCode website right now, and it's okay. Good. Okay, it's opening. And almost there. Give me a second. Okay. Almost there. Okay, yeah, we are there. Yeah, we are right there. Okay, now let's share. Can everyone see my screen?
Yes.
Good. So this is the code I just explained to you about. Yeah, merge case sorted list. It's actually elite code hard, but it's actually realize it's not hard, right? Like we just discussed this thing. Like it's actually not hard, right? Like so this is a wrapper class I just talked about that we defined, and you are done. You are there, right? So what do we do? We said we put everything inside our priority queue, right? But before we put it inside, our priority queue needs a way to compare them. So you wrap it around, right? Like you just wrapper, right? So what does the wrapper class do? Just as just set the node to be node, then less than this, just a danda method, then like this, right? So now you're not putting the original linked list inside, rather you wrap it, right? You wrap it with some new superpowers, right? Those superpowers is because if you look at the class node, if you look at the list node definition, it has no way to compare them, right? Like it's just def init, right? But now you want it to be able to be compared, right? That is why you're doing this. Now, assuming, right, like LeetCode already has their own default implementation, but one thing we could have done was we could have done this. Like, assuming we had access to like their code base, we could have done this, right? And then it'd be like self, then other, right? Then we could have been like return self.file, right? Is less than other.val, right? Assuming like we had this, right? Then we wouldn't have to, do like, then we wouldn't even need this guy, right? Because if it has this, if a class has this, that means it can be what do you call it? It can be compared. But then the class node they gave you had none of these. So that means that the priority queue cannot know how to compare them. So you're like, okay, then I'm going to create my new class. My new class is simply going to wrap around that node that they are giving me, and I'll give it that new superpowers, right? And that's basically it. So so that's how you actually use it. So you load everything inside, right? And then what do? You pop out the current node, right? Because it's a main heap, it's a minimum priority queue to give you the one with the lowest value. Then you join it to your result. Then you move that one forward, right? Then you move your result also forward. Then you just then you do and then after that, you are done. Yeah. Any questions? Wait, does it make sense? Isn't it so pretty? And it's least code hard. See, it's not so bad. Let's see companies have asked. Recently, Amazon asked, Google also asked, Tesla also asked, Facebook asked, Microsoft asked, Apple asked, blah, 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 blah. 2 years ago, Snapchat, Nvidia, Zoom, Goldman Sachs, Yahoo, Oracle. Yeah, it's not actually the worst. Yeah.
So
Yeah.
you see that one retains a boolean, right?
Let me share screen again.
The Danda function retains a boolean.
Yeah.
Okay.
Yeah. So yeah, so that
The Danda function is retaining a boolean.
Yeah. So how comparators?
So how do we compare booleans?
Good question. So this is how comparators work. I actually didn't go much into this the last time we did like 3 months ago. So let me show you how comparators work. So this is how comparators work. When you take 3, right? When you take 3 and 4, right? So
Okay.
they're like, so they'll take 3 and 4. So that will be self and other, right? Self and other. So what it does is that self is equal to 3 and other is equal to 4, right? So this is what happens here. So we are executing this guy, right? Let's just copy this guy and bring this guy here. So right. So this is what it's trying to do. Then to do that, so this thing, this LT means less than, right? So here you want to compare, right? So less than. So it's like return self.node.val is less than other.node. So that's like return 3 is less than 4, right? So self is 3, right? So if 3 is indeed less than 4, it will return true, right? And then you get 3, 4. Does it make sense to everyone? Like less than, this less than. So if 3 that itself is less than 4 to return true, right? And then to give you 3, 4. There's also greater than. There's also equals. So underscore GT. There's actually there's also GE. There's also like underscore GE. There's also underscore EQ, and like so on and so forth. But you don't usually like implement these. You can actually look up more Danda methods.
Okay, so so it doesn't just give you the boolean; it gives you the boolean and then the numbers in order.
Yeah, so it uses the boolean.
I didn't get a password.
Yeah, so it uses the boolean to do the comparison. So this is how it does the comparison. So let's go through how it does the comparison. So it will take 3 and 4, right? Then it will be like, I think 3 should come first. So like, let's see how the program is thinking. It's like, it says, I think 3 should come first. So I think 3 is less than 4. So, but then it needs to make it, so it will come here, it'll be like, is 3 less than 4? It's like true. If it's true, then I'm correct. Then I'll continue. Now I'll take 4 and 5. I think 4 is less than 5. So 4 is self. Then, so if it's true, that means I'm correct, right? Then let's say it takes 5 and 1, right? So it's self and other. It's like, I think 5 is less than 1. Then it's like, oh, oops, 5 is not less than 1. So this is going to return false. If it returns false, that means you have to swap them, right?
Okay, so the Danda function is always returning a boolean depending on the values of the numbers, right?
Yeah, exactly.
So how does that fit in with the rest of your code? Like, does it add those booleans to your queue? Your priority queue or what? Like,
also, so what the priority queue is going to do that the priority queue, right, has the linked list like this, right? So this is how the priority queue has it, right? And then for the priority queue, so but you notice that for a linked list, you only have access to the head, right? You only have access to like the head node, right?
Yes.
So you only have access to 1 and 3, right? So what the queue does is that it tries to then compare 1 to 3, right? So it will be like, I think 1 comes before. Yeah, so that's what it does. So if you look at those who code in Java, will come across comparable versus comparator. So it's actually a comparable interface. So assuming you're creating a class of movies, right? But then you want your movies to be compared, right? You want the movies to be compared. So look at how they are trying to compare the movies. So I want to compare them based on year, right? So that's like, if my year is less than your year, right? Then that means that I should become first before you, right? Because with Python usually just works over, but Java will force you to do many of these things. Yeah. So see, it's a little hard, but you realize it's not really that bad. And you can do the other solutions we did also. I've actually done this some time ago in 2021. That's what I did. Like the first solution I told you about, where you the first solution I told you about, where I'm like, just take any two and then merge, right? Like we define a function to merge two lists and just, take any two, then merge, then take the result and merge, and then take the result and merge. It works. Well, yeah, exciting stuff. Any other questions? Any other? Yeah. So I think we're actually in good shape, and we're behind time, but we are some way somehow we're almost done with heaps and priority keys. We're actually not done because we also have to go over how insertion, deletion, and searching works. I mean, insertion. I mean, we only care about getting the topmost elements right in the tree, and that is simple to get. But we also have to talk about how deletion works. In other words, when it gets to that root node, who comes in its place? Because if you remember, we said that the order of the elements below the root node is kind of like random, right? Like nobody, like there's no order for it. So there has to be an algorithm to help you, get that element, and we'll go over it when we go over it next week. So, and then that's when you will understand why the tree has to be complete. So you see, we said the tree has to be complete. We will explain why the completion matters when we go over that algorithm. So please, if you came late or whatever, you've not watched any of the recordings, please do well to watch them. The last thing, Julian will actually touch on it more, God willing, next week is what do you call it? Problem solving and study sessions we'll be having. But we are out of time, so I'll not touch on it now. So Julian will touch on it, God willing, next week. But I'll do also upload the recording. I've not uploaded last 2 weeks yet. I was very tight with exams and everything. And now I don't even have access to stable internet. So I can't upload it now also. I'm using someone's hotspot right now. God bless them. So we'll upload everything. We'll upload this week's practice problems also. Please do well to solve them. If you have any questions, just ask in the group. Any questions? Any questions? And please try to solve the problems. Like, watch the videos. If you get stuck, just let us know. I think this week we can have a meeting with a couple of you to go over a few questions. But try. It's actually not that bad, right? It's not that bad. We have 2.5 months to go. Let's do our best.
Sorry for interrupting. Wait, can I ask any question at all?
Yeah, you can.
Yeah, I just want to ask about like internship. So what kind of job that interns do? Do they use like data structures to implement stuff?
Yeah, very good question. Yeah, so you actually use data structures really in the real world. So if I speak of mine, okay, I think I can. I'm no longer there. Okay, so I actually did mine last summer with Facebook Meta. And well, I worked with Meta, but I actually worked on the Facebook thing. Okay, so I was supposed to, like, I built a full stack application, right? Where I had to take data from the backend. We use GraphQL. We don't use like RESTful routing, like app.get, app.post. We don't do those things. The laser knows RESTful routing. We don't do that here. We use GraphQL. So the data is like this bunch, like this whole huge information, right? And you're building a scalable system for a company like Meta, right? Like Facebook, because like WhatsApp may use it, Instagram may use all these things, right? So it has to be very scalable, right? Very efficient. So you have to use efficient data structures, because assuming it's like 1 million data, right? Like it's 1 million entries, and you use an array, right? That's like every set is going to be O of n, right? Which is not really efficient. Like imagine you use like 4 nested for loops. So it's going to be O of n to the power 4, which is really bad. So if you know data structures and algorithms, you're like, okay, let me use a hash table. Okay, let me construct a new object and everything. So that's one way which it really comes in handy. We're going to deal with like very huge data. And the question you ask yourself is, what is the main operation? Is it going to be just searching? Is it going to be insertion? Is it going to, am I just going to need one value at some point? Is that value like the minimum or the maximum value? Then begin to think along the lines of heaps and priority queues. So that's one way you need them. There are times you also need them. It's when you're creating your own custom things. So sometimes like the data isn't in some good format for you, right? But you have to create your own classes. Then inside your classes, you define how things you. So I don't remember if people remember the hash table problem you solved. You have to design your own hash table or your own hash sets, right? You come across those questions a lot in here in the real world, right? You have to create your own class. Then your class will have fields to store your data, and inside those fields you have to decide: am I going to use a hash table? I'm going to use a stack with queue. So that's one thing. The other thing also is programming. I think one thing you actually gain from this practice is programming, right? Like you learn to write clean code and concise code. Like sometimes me myself, I look at code I wrote like 2 years ago and I'm like, bro, this code is so bad. I don't write this code anymore. So as you practice more, learn new algorithms and everything, I feel like you write less code. Like people won't come to your code base and they see you writing if flag is equal to true, right, bro? Like you don't write that code, just write if flag, right? So I think that's the other take you get. Like you get to write more code, you get to see other people's code. Like you see someone's code, they've written if this return this, and if this return this, and if this return this. But you know that they could have just done just one variable, then with just one return statement, right? But they have like 10 return statements, which isn't because the code writing may be used by other engineers and everything. So I think it really helps. I think the last thing, which is a bit rare, is in systems, right? Where you have to design like a file system, your own database. Companies build their own databases, like Amazon. They use what do you call it? Amazon has DynamoDB. At Microsoft, they have the Cosmos DB. At Google, there's Firebase. At Meta, oh, that's sad. I don't know the Meta one. But then they use SQL to some extent, right? And database designs, you use data structures and algorithms. So they use B+ trees. They use like trees. They use linked lists. The person who is linked list, yeah. So these are actually things you get to really use in the real world. But usually in daily lives, I think hash tables are more used than maybe arrays. Then I mean, like from my experience, like I'm not experienced enough, but from the little I've built, I think yeah. So it's good to know them. But I think the biggest take is how clean code, like how you write code. I feel like if you get to practice a lot and read people's code, you get to see like very, very nice ways of writing code, right? You're like, wow, this thing existed. Like yesterday I saw another code, I'm like, wow, this is really nice. I even forgot it. I think that's the biggest take. You write clean code, you reduce code redundancy. And I've seen some people's code and the if else are like, a whole bunch, right? So I think that's like the biggest take.
Okay, so one more question. So for the functions and classes that you'll be implementing, I mean that sometimes you may write your own functions or helper functions and like classes to solve the problem. But then are there like classes with specification, like functions with specification already written for you?
No. Yeah, I know. Yeah,
That's right.
I know most of us in our schools, in our assignments, our teachers give us like function stubs, right? Like they tell you the functions, right? They write the specification. Honestly, in the real world, like the little experience, like last summer, the stuff I built, like I mean, they'll give you a document about what the product you're building or what you want to build, right? But no one is going to tell you call your function this, add this specification. Like no, like no one has. I mean, maybe. I mean, if it depends on the internship also. But like I had like nothing like that, right? Like everything is up to you. Like you own everything. Like if there's a function you want to write, you write it. But the cool thing is sometimes functions are already written for you. You are just filling in. I mean, like the thing exists, but the functionality you are adding like requires you to maybe add some lines of code to it. But breaking down functions, and honestly, we don't even write specification that much. To be honest, when I like went at Meta, I remember last time I saw a function with documentation. Why? They use good naming conventions. The function name is the name, right? Like you don't call the function name, the dog jumped over the horse. And then write specification. This function has two numbers, A and B. Like, no, we don't do that here. Right? So that's why you have to learn to build things from scratch. That's things I tell people. If you follow a tutorial to learn something, don't end there. After you're done 1 or 2 tutorials, try to do your own thing from scratch, to write your own functions, to break down functions. I'll actually upload a video that will help probably people who want to learn how to write things like functions, because functions are so important. Like functions are like the core of almost like much programming we do here. So you have to learn how to write things from scratch and not always depending on stubs. Stubs really don't help. I took programming class without even knowing how classes work in the real world till my first internship. So yeah.
Yeah, thank you very much.
Okay, so I have
yeah.
a question.
Yeah.
So would you sacrifice pace over speed or speed over space?
Over space. Oh, good. That's a question. There are a lot of cool things, right? Like there are lots of cool things in the programming world, right? And I don't know, I just get excited about them. But yeah. So that let me just show you something. There's something called the cap theorem, right? I told my internet what the works, right? So what's the cap theorem? So the cap theorem is simply, it's something distributed, right? Distributed systems. That tells you that there are basically things in computer science that are always going to, challenge one and the other, right? Something gets some situation where things are just opposing one another, and they tell you, oops, you can't have everything. So this is why it's telling you here that whenever you're building a very scalable system, right, you're faced with 3 challenges, a distributed system. One is consistency. The other is availability. The other is partition tolerance. Consistency is like blah blah. Just check the English names as it is, and they're telling you that there's no way you can have all 3 together. So you can see there's no intersection of all the 3. Like there's nothing like this. Always have to sacrifice one. You can get 2. You can get 2. Sometimes we get to that point we can get all 3. Sometimes this translates to time and space complexity. That sometimes you can have everything. Best sometimes you can have one and sacrifice the other. But from what I know, generally we go for time, right? Because I think it's cheaper to get space, right? Like space is cheaper compared to time. I think that's what I remember. Um, and so time is usually more prioritized, right? Because space is just what, kilobytes, megabytes, I don't know, bytes, right? But time is a more extreme thing, right? So when I took an analysis of algorithms class, I remember last time they deducted me points for wrong space complexity, but time they'll take away points, right? So time is prioritized over space, and space, like, I don't know any algorithm that uses like O of n to the 3 like space complexity. It's really just linear space. Unless you're doing something, unless you're doing something like recursion. But recursion, if it's not tail recursion, right, and the cluster grows, it can actually fill up your, what do you call it, your stack. When you say programming language like C, can have buffer overflow. Well, that's why we don't really see here. Yeah. So space becomes tricky if it's like your thing is just growing to fill your entire core stack, and then you like no other process can run. And if you use a programming language like C, if you create an array of size 10 and you fill it with an array of elements like with 20 elements, it can overflow and override your other data. So because something buffer overflow, and that's a system people use to hack people, right? Like buffer overflow attack. People use it to hack people. So if you read briefly, it says when an anomaly program, while writing data, buffer overruns the buffer's boundary and overwrites adjacent memory locations, right? So assume your password was stored in this adjacent memory location, right? And I know exactly it. I can just write code to just overflow that place, and I end up, attacking your system. Then I get control over your system. So space becomes an issue. But this is like, it's a very common, like C. People actually do this when they do C programming. But I know generally we go for time, right? Space is relatively cheaper. Makes sense?
Yeah, thank you
Yeah,
very much.
like,
Yeah.
and also the general statement is you can always buy like 1 extra terabyte of hard drive, but then you
Yeah,
can't buy
exactly.
2 more seconds of time.
Exactly. Space is relative to
So,
time. Like one cool thing, people should look up NVIDIA's new systems, bro. It's so cool. NVIDIA is just an amazing company. Yeah, they're building like things, bro. It's like their systems are so fast, and it's just so cool. Yeah. Anything else? So yeah. So please, 2.5 months left. Honestly, trust me, I feel like everybody here is really on top of their game. Like when I said this thing, as I said, last 2021 May, I didn't know any data structure, I didn't know any algorithm. The only thing I knew was some Python and some HTML and CSS and stuff. But I had to spend my whole summer learning all these things, every single one of these things, and by God, these things worked out. But some of you already know some data structure, some of you know some algorithms, some of you even have materials curated for you, like this workshop and everything. That teaches you more than what textbooks teach you. Like we combine so many things. So please take advantage and learn. 2.5 months to for recruiting to be very heavy. Just don't waste time. Like just don't, right? Just do your best. If you have any issues, just hit us up and we will schedule meetings with you. Yeah, so that's it. Thanks for coming.
and one last thing I want to add is I know Cornelius has spoken a lot for like 1 hour 30 minutes. It's a lot of information. Even me, to an extent, I can say it's a lot of information. I would just say take your time, review it, right, and know how, just absorb it bit by bit. And it's fine if you don't understand everything right now.
Yeah. In other words, it means I like talking. So, yeah. And yeah, Julian will talk on next week on the live work sessions we'll be holding over the summer. Like we'll just start the Zoom meeting. You can come in, we can discuss problems, we can learn together, like anything you want. We just want people to be up on the game because we just have 2.5 months left. And yeah. Okay. Julian, anything else? Wisdom? Anything?
No, I'm good.
Okay.
No.
Okay, we are done then. Bye. Yeah.
I want to ask a question.
Yeah.
You see, in assessing whether the time complexity of an algorithm, right?
Yeah.
Okay, let me use this way. Let's say you have a for loop, and inside the for loop, you call a function, right?
Mm-hmm.
Would you say that function, function's complexity is O of n because it's in a for loop, or
no,
the function that the for loop is in is rather of n?
Yeah. So let me show you a cheat in time complexity that I sometimes use. So when I saw a question in an interview, right, and I'm not so sure of the time complexity, this one cheat I use. Let me show you. So when they ask for time complexity, they're basically asking the time complexity of the algorithm, right? Algorithms are not functions. Functions are just a way to package your algorithm, right? Like this is an algorithm, right? What's this algorithm? It's just an algorithm to merge any two linked lists, right? Like this, your algorithm, right? Then you're like, okay, let me put this in a function so that I can call the algorithm many times, right? By just giving it any two linked list, then it will merge. But let's assume I don't know the whole thing. So one thing I usually do in an interview, if I'm not so sure, is I will give you the time complexity of the parts of the algorithm, or the parts of the code. So I'm like, okay, this while loop is going to take, so you can actually start from the inner part, right? So I'm like, okay, this comparison is constant time. Just checks if L1 is less than L2. Okay, then this is also constant time. But then here I'm going through the linked list, right? Going throughout L1 and also going throughout L2. So it's going to be like linear. I won't even say O of n, because boys is O of n plus m. I'll be like, okay, so that's linear time. Then I'll come here, I'm like this. Then I'll come here, I'm like this. If at the end of, giving out the parts, right, I'm very sure of the whole like function, then I'll tell you the function one. That's what I'm trying to say. Ideally, what they want is for the algorithm, that's like the whole function, the time complexity. But if you're not so sure, nothing prevents you from just telling the time complexity of the parts of the algorithm, right? So I'm like, here, this is constant time, this is going to be linear and everything. Maybe when you add everything is quadratic or something. Even if you're not sure, right? Like, don't go and bother yourself and be like, sometimes it is O of n plus. I've seen very scary time complexities, trust me. One I saw recently was nk log log of nk log nk. Bro, how are you going to put this, right? Like, so I would say you can just use the words linear, can use the words quadratic, right? Like, these words can really save you, right? So you're like, okay, this is linear time, because linear can mean O of n, linear can mean O of n plus m, linear can mean, a couple of things. So just break it down. So, well, L1, okay, so this linear time, they be like linear in the size of L1 and L2, this and this, that. So that's one cheat you can play. But ideally, what they're asking for is the time complexity of the whole function, of the whole algorithm. But if you're not sure, just tell them in parts. One way I sometimes did that, some people finish coding the problem and then they tell you the time complexity. But if you think it's tricky, as you code, discuss the time complexity along. So I'm like, so here I'll go through, so I'm merging these two lists. I'll go through L1 and L2, and that's going to take me linear time. Then just go at the end, they'll know you already discussed time complexity and you're safe. So, I mean, with practice, you get to, like, no one told me these things. I just adopted them with time. So, but if you do mock interviews with us, we'll walk you through some of these things. So, yeah.
Thank you.
Yeah.
So,
Yeah, go ahead. Wait, was Asante trying to speak?
no, sorry.
Oh, okay, sure, no problem. Yeah, so everyone, that's all. Please do want to solve the problems when we upload them. Please try. Please, we beg you, just try. Okay, so we are done, and see everyone, God willing, next week, Sunday. Bye.
All right. Bye.